Hi everyone, welcome back to the Comptia Network Plus course, Unencrypted Channels. If it isn't clear to you by now, in any situation where sensitive data is being transmitted, attention should be given to the type of channel across which the data is travelling. When no other method is available, IPsec is a network layer protocol suite that can be used to provide end-to-end protection of any data that resides above the network layer. Many protocols provide the ability to control access through authentication. However, while some protect the confidentiality of the process by hiding the credentials as they are exchanged, others do not. For example, Telnet, a protocol used for remote command line management of devices, transmits credentials in clear text. Secure Shell SSH does not. Another example is Password Authentication Protocol PAP, one of two authentication options offered when a PPP connection is being set up. PAP transmits credentials in clear text, while Challenge Handshake Authentication Protocol CHAP, the other option, uses a process that never sends the credential across the network. You should never use a protocol that transmits credentials in clear text. TEMPEST RF Emanation. Spying on information systems can be accomplished by capturing and analysing leaking emanations of things like radio or electrical signals, sound and vibrations. TEMPEST is a National Security Agency specification and NATO certification that addresses methods of spying and used and how to protect against them. Distance shielding, filtering and masking are used to protect equipment from spying. The TEMPEST standards are used to describe the level of protection as a system is certified to provide. Malicious users. Damaging activity on your network can come from both inside and outside the network. In the following sections, we look at the two types of malicious users you will encounter and an operation often performed in the execution of their mayhem. Trusted users. While we would like to think that all of our own people can be trusted, that's not often the case. Even your trusted users can go to the dark side with the proper motivation. The following are among the motives that can turn a trusted user into a malicious user: perceived slight by the company, jealousy of other employees, monetary reward. The real danger presented by a trusted employee who turns malicious is that the employee is already inside your network and probably knows quite a bit about it. This is the reason for the following the principle of least privilege, which prescribes that users be given only the resources required to do their job. Untrusted users. While it may take untrusted users or users outside your network a bit longer to make their way into your network, once they get in, they will probably have a significantly higher level of skill than a disgruntled employee has. Discovering and penetrating your network from the outside takes some skill. The best mitigation for these attacks is a combination of perimeter defense, keep them out, and a strong access control at the point of resource access to prevent access to devices holding information. A multi-layer approach works best. Packet sniffing. One of the basic tools a hacker will possess is a protocol analyzer or packet sniffer. These devices capture raw packets off the network for analysis. Normally, a device will only process packets that are destined for itself, but this software places the network places the network interface of the hacker's device in promiscuous mode, which means it captures all packets on the network. This software can also be used legitimately to examine your network traffic for things that should not be there. Figure 410 shows an example of the output of a packet analyzer Wireshark. In the output, it can be seen that packet 4 failed a frame check sequence, which would require it to be sent again. While the list of packets captured is displayed, you can click on any packet and examine it in detail. If the data is in clear text, you will be able to read it. Buffer overflow. When programs execute, they write commands into memory or to a buffer. Well-written programs allow a certain location and or amount of memory space for these commands to execute. If a hacker is able to inject a command that overflows the amount of memory allocated and the command is able to execute with the proper security privileges, the hacker could execute commands that would not normally be allowed. They may be able to take control of the machine and create havoc. A number of well-known exploits such as Code Red Worm employed buffer overflows to create mayhem. The way to prevent buffer overflows is to include input validation into programs and mitigate the possibility of them occurring. DNS poisoning. DNS clients send requests for name to IP address resolution queries to a DNS server. The search for the IP address that goes with a computer or domain name usually starts with a local DNS server that is not authoritative for the DNS domain in which the requested computer or website resides. When this occurs, the local DNS server makes a request of the DNS server that does hold the record in question. After the local DNS server receives the answer, it returns it to the local DNS client. After this, the local DNS server maintains that record in its DNS cache for a period called time to live (TTL), which is usually an hour but can vary. In a DNS cache poisoning attack, the attacker attempts to refresh or update that record when it expires with a different address than the correct address. If the attacker can convince the DNS server to accept this refresh, the local DNS server will then be responding to the client requests for that computer with the address inserted by the attacker. Typically, the address they now receive is for a fake website that appears to look in every way like the site the client is requesting. The hacker can then harvest all the name and password combinations entered onto his fake site. To prevent this type of attack, the DNS servers should be limited to updates they accept. In most DNS software, you can restrict the DNS servers from which the server will accept updates. This can help prevent the server from accepting these false updates. Wireless threats. The proliferation of wireless communication has introduced a number of security challenges that are unique to the wireless environment. Some of these threats even take advantage of the security measures that have been created to protect wireless networks and hosts. Wireless threats such as WEP and WPA cracking, discussed in the following sections, remind us that network attackers never stop evolving their methods and that constant review and adaptation of security measures are required to maintain security in the network. War driving. War driving is the oldest wireless threats and perhaps one of the easiest to discourage, although you can't defeat it if a hacker is determined. The attacker simply drives around with a high-powered antenna connected to a wireless laptop scanning for networks. The networks will be listed by the network name SSID. in the wireless client software, and depending on the software, the channel and security measures in use will also be displayed. If the network is not secured, the attacker can connect to it. This is not just a matter of stealing bandwidth for internet access. Once connected, the attacker may be able to proceed on into your wired network as well. They can then attempt other attacks such as port scanning and peer-to-peer attacks. The point is that they have completed the first step in the hacking process, which is penetration. War driving cannot be entirely prevented, but you can make it harder for the attacker. One of the simplest things to do is limit the transmission power of the AP, and that the signal does not go any further than required. Additionally, if you set the access point to not broadcast the SSID, the name of the network will not appear in the display when they scan for networks. This means that to connect, they will have to know the SSID and create a wireless profile specifying it. If an attacker is determined, however, they can learn the SSID by using a wireless protocol analyzer or sniffer to capture raw packets. This is something you cannot prevent without turning off the AP. When you set the AP to not broadcast the SSID, it will remove the SSID from packets called beacons. These are the packets that populate the display when you scan for networks, but the SSID will still be present in many other packet types. In most cases, hiding the SSID will be sufficient, because if an attacker doesn't see your network when scanning, they probably won't be motivated to use the sniffer. War choking. War choking is really just an extension of war driving. The hacker simply writes the SSID and security employed on the sidewalk or wall somewhere near your facility, sort of like advertising, "Here's a wireless network," to anyone who recognizes that code. Most of this type of activity has moved online, where websites have sprung up that allow hackers to post and share these networks and maps indicating their location. WEP Cracking, Wired Equivalent Privacy, is a security protocol created in the early years of 802.11 development. Was designed to both authenticate users and encrypt the wireless data they transmitted. It uses the RC4 algorithm in the encryption process. Soon after its adoption as a security measure, it was discovered that due to the weakness in the way the algorithm was employed, programs that became widely available on the internet could be used to crack the WEP key. Once the key was shown, it could be used to decrypt the data. Because of this, WEP is no longer considered to be a sufficient security mechanism in any situation where the data is sensitive. WPA2 Cracking. After WEP cracking became an issue, the manufacturers of wireless equipment were faced with a problem. The IEEE was working on a way to create a new security standard, which became known as 802.11i, but were moving at their usual deliberate pace. In the meantime, companies were not deploying wireless networks because of security concerns. The Wi-Fi Alliance created a temporary solution called Wi-Fi Protected Access that was an improvement on WEP. Soon after WPA was rolled out, it was discovered that it could also be cracked. Cracking WPA required more effort than cracking WEP, and it required what is called a dictionary file, a file of words that could possibly use as a password. It also required that a passphrase or password be a word in the dictionary. Finally, it required capturing a large number of wireless frames, and the cracking process took a lot of time. Keep in mind that this type of attack is effective on any password-based systems, including Wi-Fi protected access to WPA2 when it uses passwords. But the point is that if the attackers had good reason to believe they were capturing valuable data, it could be done. Therefore, WPA is not considered good security unless it is employed as WPA2, which is based in the secure 802.11i architecture. I'm going to leave here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.